Welcome back to ECE 501B. Do I need to dim the lights on the screen, or is that acceptable? Is it visible for you with this all lit up? You're okay with that? You might notice in the announcement that there's one more thing that's been added. You now have a homework assignment that's due, and you can submit that to the Dropbox or turn it in hard copy here in class on, oh, you won't be able to do it on that day. That's a Thursday. But we will meet again on Wednesday, and if you want to submit your homework then, you may. But I'm giving you another day with office hour help, for example, to complete this first homework assignment. That's the idea behind that. What I want to do today is try to finish chapter 1 of Axler, and that's going to involve then, well, let's just sort of remind ourselves of where we're at, try to keep thinking about vector spaces, and maybe try to keep those more general than this column of real numbers. We may want to think about vector spaces in more general terms than that. But really, it's a set with two operations. You're really thinking of three things. It's a set, and then you have an addition and a multiplication, in quotes, that work on those set of objects. And we'll try to give some more examples. Then we will state the properties that are listed in the textbook as propositions 1.2 through 1.6, just so that we've seen them. You know that what they look like and what they somewhat mean. We won't go into them very much. They are proven in the book, and you'll want to look at those proofs. We'll talk a little bit about proof techniques, which the outline of those proof techniques is provided in the inside covers, both front and back, of that book that I talked about last time by Daniel Solo. We will go through a proof of one of those propositions, 1.3, and that will be a proof by contradiction. That will mean more maybe after we've talked about the different kinds of proofs. We will then look at how we can maybe separate these vector spaces into pieces or subspaces. We'll define that concept and discuss that. Basically, it's a subset of your original vector space, but the subset enjoys all the properties of a vector space. If that's the case, then it's a subspace. So I have sub floating around in several ways, but there's a distinction between a subset and a subspace, and that's what I want you to keep clear. And we'll finish up chapter 1. Hopefully we will get somewhat there with how do we build up vector spaces. Now that we've torn them apart with subspaces, can we add these pieces, these subspaces, into sums and direct sums of vector spaces? That's the idea. Where were we? This is hopefully what we talked about last time in a graphical depiction. We talked about a vector space. This is a review or a recap. And again, that is just a set of objects with two binary operations. And the two operations are an addition and a scalar multiplication. And that addition is with respect to a vector. And that vector is not necessarily this tall, thin column of real numbers. It could be a 2 by 2 matrix, and that could be a vector. A vector is this object in the set that we're drawing from to create our vector space. We also have this scalar multiplication, and that scalar is coming from the field, and that field we might denote by this sort of script F, but that script F is typically coming to us as the real numbers or the complex numbers. That's our definition of a vector space, and a very simple or straightforward vector space is the real line. Just keep that in mind. Realize that, wait a minute, let me just think about a particular example. Can I draw the real line? That's now a vector space. What do I want to think about in terms of maybe these properties or ideas that are being discussed in class? So what you should be doing then is, what I'm hoping is that we want to remember to think of a vector space like more of a collection, let me say collection, in which any linear combination makes sense. So we want to be able to linearly combine these objects coming from a set. That's a vector space. Meaning that's maybe more general. So remember to think of vector spaces like that, and not exclusively like this column of real numbers, and not like a collection well, let me say, of columns of reals. Now that I make that claim, sometimes it's nice to actually go back, though, and think about these weird vector spaces like a column of numbers. So you want to keep both concepts in mind. So although we still want to be able to draw from that strength that we might get from our memory of vectors being this column of reals, although it can be let's say helpful to keep these columns in mind. Let's look at some maybe more general ideas of vector spaces. And one of those is the set of all polynomials. And if you're looking in your textbook, that's talked about or introduced maybe for the first time on page 10. And my notation may be a little bit poor in terms of that's supposed to be sort of a script P for polynomial, and it's working on elements from this field where F is either the R's or the C's in general. So now we have this collection of polynomials, and if you wanted to think about that, you could maybe build that up from this unending sequence of powers of z, where these coefficients, etc., belong to this field of numbers, and z is also any value in that set. Now, we could also, if you wanted to, you could think of another more specialized, and even we'll learn that that would be a subset of this. This is now a vector space, this set of all polynomials, but we could also look at a set of second order polynomials, and let's just specialize that to say over the real numbers. In this case, we now have, let's say, this script P sub 2, and it's pulling these, let's say, the functions x from the real numbers. And now we could say that we are looking at a sub 0 plus a1x plus a sub 2x squared, where the a sub 0, a sub 1, and a sub 2 are coming from the reals, as are these x's. And now we can maybe make this connection. Maybe here's this polynomial and we're going, I don't see that as a vector space, or I'm having trouble thinking about these concepts. Well, we can actually relate this, or can think of this set of second-order polynomials as if it were a vector in R3, meaning we can now think of P sub 2 of R like R3, meaning if we simply pulled something out of this second-order polynomial, let's call it P of x, that arrow then, I'm using that to say corresponds to a vector a sub 0, a sub 1, and a sub 2. And now if we wanted to define a sum of maybe a polynomial p and a polynomial q, we could also think of that like this vector of a's and b's. And how do we add those up? Well, it would be consistent to how we might add up these elements in these column vectors. We are simply adding up the coefficients in P and Q. And if we did a scalar multiplication, that's the same as scaling each of these coefficients, but that's equivalent to scaling the elements in this vector of coefficients a0 through a sub 2. So you can start to think about, oh, well, maybe the same ideas or concepts for a polynomial with functions 1, x, and x squared, I can think of as this column of coefficients, a0, a1, and a2. If that's not enough, suppose we look at this vector space, a different vector space. Again, I'm trying to get you to think of these concepts or ideas as more than just column vectors. Let's say that we now want to look at the vector space of 2 by 2 matrices. Meaning now we might say, okay, here is our vector space, M sub 2 by 2, which we can now build up as A, B, C, D, such that maybe we want those A, B, C's, and D's to be drawn from the field of real numbers. And that's maybe this typical 2 by 2 matrix that you're used to thinking of or playing with. We could also say that that corresponds to, or this is the same as what? What sort of vector might we think of if we now had this 2 by 2 matrix A, B, C, D? What kind of a vector would that look like? We could build up a specific matrix. We could replace all of these A, B's, and C, D's with any real numbers we wanted, and that would be a 1, 2, 3, 4, for example. But now if we wanted to think of that like this column of real numbers that I said, now we could just stack up, let's say, those rows, or transpose the rows, and then concatenate those columns now on top of each other. Meaning this could be viewed as living in a space R4. This is a four-dimensional space. Those four numbers, A, B, C, and D. So this corresponds to, or the same as, R sub 4, where we might have this A, B, C, and D living in R4. Is that making sense? So that's another vector space, is this M 2 by 2, and we can generalize that. We could say that we might want a vector space M sub Michigan by Nevada, M by N, where those are whatever integer values we want them to be, and now we have another vector space. And that would then obviously influence this corresponding column vector that might be in R, some other big dimension. What about another possible vector space? Suppose that I said, okay, here's a vector space V that's going to be denoted by some function f such that we take the natural numbers into the real numbers. This is now the set of all functions that take natural number arguments into real numbers. This is now a function. Trying to sort of label my notation. This might be our set of natural numbers. That's what we use to count with. I can kind of keep track of those sometimes, 0, 1, 2, etc. And here are our reals. Let's look at an example of this. Suppose that we said, well, let's just create or pull out some functions f that would belong to this set or to this vector space. And one of those, let's just label that f sub 1, and its argument is taking values from the natural numbers. The argument of f sub 1 is 0, 1, 2, 3, etc. And suppose that we just say, well, that's going to be n plus 1. That could be whatever we want it to be. But it needs to have n in there somewhere, probably, to be connected with the argument. And let's say that we try f sub 2 of n, and maybe we make that 2n squared minus n for its expression. And since this is a vector space, we know that we can linearly combine any of those functions in that vector space. Let's just add those two directly. Suppose we create a new function that's a part of that vector space and just call it f of n, and let's just say that's f sub 1 of n plus f sub 2 of n. And we could have scaled that by any kind of scalar we wanted if we were pulling that from our set of real numbers. That could be 2 times f sub 1 of n plus 3.726 times f sub 2 of n. We wouldn't have had to be so benign with our combination of f1 and f2. But here it makes it easier to sort of do the algebra. If we do this, we now have n plus 1 plus 2n squared minus n, or the n's now cancel and we're left with 2n squared plus 1. And we could now build up corresponding vectors associated with this just single function. Meaning now if we wanted to sort of think in terms of these columns of reals, we could build up a table of numbers. We could say, well, here's n and here's f of n, which we just computed to be, for this example, 2n squared plus 1. That one I hope we can calculate. If I substitute 0 into that right-hand expression, what do I end up with? 1. That's, I hope, okay. Now if we substitute in 1 for n, We have 3, and we can just keep going. Let me just write down some of these. If we have 2, stop me if I'm wrong. 3, 4, what was the formula? Is that 33? 5, 51, and now you can just see that we could just keep going, right? Because the argument is the set of natural numbers, and our result, the value of f of n, is this right-hand column, so that now we could think of this function corresponding to, just stack these up. But now what do we have relative to this column? How tall is it? How tall is that column? Very tall? It's pretty tall, isn't it? It's infinitely tall. So now we have this infinitely tall, but this is something that we talked about last time, I think. Was having the possibility of this infinite sequence representing these elements of a vector space. So this is another way of thinking about how you might generate such a unending sequence of numbers. It might come from a function. Well, we can generalize that to other vector spaces. For example, we could now say something like, well, what about we have a vector space V that is now F, such that we take the reals into reals. That's just a function that takes as its argument real numbers and maps those into real numbers. And that's like these functions we normally draw in terms of an xy plane. Here is now our x, here's our f of x, a generic one, and we might now think of that as something like that. And this is now one of the members of this vector space. And now we can be thinking about continuous time functions forming vector spaces and not just tall, thin columns of numbers. How about another one? What if we said, well, let's think about another potential vector space. Suppose we say W is the set of functions f that take as their arguments real numbers and map into real numbers, but such that, that's what that vertical bar means, but such that those functions are actually in such a relationship to satisfy a differential equation, that the second order derivative of that function with respect to its argument x plus the function itself is equal to 0. And that could be then defining this vector space. Now you're looking at all of these functions that satisfy this governing differential equation. And now you have another vector space. And you can combine those, since it's a vector space, with... Go ahead. Yes, so this vertical bar, the question I think was, what is this? It's a vertical line. That doesn't help much, does it? But that just means we want to have functions such that they satisfy this differential equation. That's what we're wanting to do. So that vertical bar means that we need these f of x's now we're specializing those. We only want to pull from those f of x's that actually satisfy this differential equation relationship. Now, do you remember some of these functions? As an example, what about a cosine of x plus b sine of x? That f of x, if you differentiate it twice, is going to be the negative of f. You can do that in your leisure. You'll want to go home tonight and do that. But if you now differentiate this twice with respect to x, you'll get the negative of this, and that will sum to 0. So this function now is a part of that vector space. And you could build up other functions that would satisfy that same relationship. But now that we have this, we could say, well, we know this function, cosine of x. If somebody gives us an x, we can compute cosine of x. If somebody gives us another, if they give us x, we can also compute sine of x. We know those functions. We could actually just keep track of this as these coefficients a, b. And so now we've boiled this f of x down to a 2 vector. This now looks like, or corresponds to, a 2-dimensional vector. So you can start thinking about these elaborate vector spaces, maybe more elaborate than what you're used to, but they still sort of correspond to having these 2 parameters, a and b. And this relationship is going to be true for all these a, b's coming from this field of numbers. All right, those are some examples to kind of get us thinking about vector spaces in the more abstract setting. Let's now go back, and now that we have these vector spaces, what are some of the properties that they satisfy? And I'm just going to write these down, but you can go back into your book and see those written down or typeset more, let's say, cleanly or better. But these properties are a result of the defining properties of our vector spaces. And we don't have to use these to define our vector space. These are resulting from our vector space. So proposition 1.2 is saying the following. V has a unique like I said, it's typeset better in the book, additive identity. And what's that really saying? Do you remember what they were using additive identity to mean? It has a 0 vector or a 0 element. So we have this 0 element in our vector space, and it's unique. Proposition 1.3. Every element in V has a unique, and this unique word is nice to have. Every element in V has a unique additive inverse. That means you give me an element in this vector space, and I can find another element in that vector space when added together to give me the 0 vector. That's what proposition 1.3 says. And that new element that I'm handing you, if you've given me a V, I'll give you a W. We're going to have some cheers going on here in a minute. Give me a U, give me a V, put them together. What do you have? 0. So now the scoreboard reads 0, right? If that U and V are related by an additive inverse of one another. That's proposition 1-3. And that 0 is unique in that vector space by proposition 1.2. What's another proposition that they present? Proposition 1.4. And this says that 0v equals 0 for every element or vector in the vector space. And now this is, some books probably do a better job of noting what's going on, but here this 0 means two different things on the different sides of the equality. On the left-hand side, this 0 is a scalar. That's scaling, a scalar multiplication by a vector v, any vector v in our vector space. But that scaled vector ends up being 0, a 0 vector. So if you were thinking about tall, thin vectors, and maybe we were in R3, this would be a scalar 0, and this would be a column of 3 zeros stacked on top of each other. So that scalar multiplication allows us to end up with an all 0 vector. Proposition 1.5 says that if we take any element in the field A and use that to scale the 0 vector, what are we going to get back? The 0 vector. And that's true for every A coming from our field, where the field could be the real numbers or the complex numbers. And finally, 1.6 basically sort of tells us how to find an additive inverse if we need it, and that is that -1 as a scalar times v is equal to minus v well, we could say for every v, let's say v is in our vector space, isn't it? So this is now the same. If somebody gives us a minus v, that's like scaling v with a scalar of -1. That's the same expression. And all of these propositions, 1.2 through 1.6, those can be proved from the original properties of the vector space. And so we don't have to include these in our definition of vector space. We can derive these results from the original vector space. And the way that we can do that is by proving these particular expressions or propositions. So let's now talk a little bit about how we might go about showing or proving these propositions. And we'll just talk about some proof techniques in general. And the very, let's say, overview of these proofs is found on the inside covers of this book that we talked about, which was optional by Daniel Solo. Now, in terms of a proof, let's just think about all of these propositions or corollaries or lemmas as theorems right now. So now they're all theorems. They have the same weight, so to speak. That's the only reason why we have different terminology, but they're all, let's say, theorems. And this now is basically a theorem is saying that we have some statement that yields another true statement, which typically we might think of this first statement as the hypothesis, and that yields the conclusion. Meaning it might be easy to show that the hypothesis is true. And if we've now proved this theorem, then maybe it would be difficult to always be showing that that conclusion is true. But if we've proven the theorem, now if we can simply say, oh, this hypothesis is true, then we know that this conclusion follows. So this hypothesis yields the conclusion, or we might get even more concise and say, oh, statement A implies statement B. Or you might see this written as if A, then B. And that's not the same as the converse. The converse is not necessarily true. The converse is if B, then A. And that may not be true. So we're concentrating on statement A being true, implying statement B being true. And what are some ways that we might show that? Or some proof techniques? One is, I'll just say, a direct proof, where we start with A and we simply continue to evolve that A, that true statement, into the other true statement, which is B. So we start in this approach, we start with statement A, and progress through the process to showing that statement B is true. Now, to do that, it may not just fall straight out. You may actually need to work from both ends. You may want to start with A and start with B and start building from the back and building forward and see if you can meet in the middle. So this, in the book, they call this the forward and backward approach. You may then want to start or want to work from both ends, which are A and B. And this is then this forward-backward approach. And that's going to be maybe familiar to you in the United States from your high school geometry class. That's maybe the approach that you used most of the time. You start with your given expression or statement, and you just linearly progress down to the concluding statement or the conclusion. What's another approach that we could take to prove if A, then B? We could use contradiction. And that approach, then, what we do is we start with this true statement A, and we start with the negative of the end result of our conclusion. We start with A and not B, and with those two statements, we progress to try to derive a contradiction. And if we can end up with a contradiction, then we know, oh, not B is actually false, and so we've now proven it to be true. So we start with A and not B, and try to derive this contradiction, or a false statement. 1 is equal to 2. That's false, so there must have been something wrong with our original assumption, and so we can conclude that A does indeed imply B. What's another one? Proof technique. A proof technique called the contrapositive. That's a big word. You can go home and impress your friends with contrapositive. What does that mean? Well, now you're sort of working in contrast to the positive direction. Now you actually start with the negative of your end, or the negative of your conclusion, and so you want to show that that implies not A. And you can work through the truth tables to show that not B implies not A in a truth table format is equivalent to A implies B. So if you can show that not B implies not A, then you've proved A implies B. With this approach, then what you do is you assume, or you start with, not B, and you progress to show not A. And again, if you want to do that, or if this is not making much sense to you, go back and just set up the truth tables and show yourself that not B implies not A is equivalent in logic to if A, then B. One more proof technique. And this one is if you have things maybe indexed by the natural numbers. And it's a proof by induction. This now, you basically prove the base case, and your base case typically is maybe with n equal to 0 or with n equal to 1. Then you will have some expression involving n. You assume that that expression is true for the case with it equal to n, and this is actually called the induction hypothesis. And then what you want to do, assuming that the formula is true for n, you want to show that the formula is true for n plus 1. And you can use the fact that you're assuming that the formula is true for n. And if you can do that, then you've proven your result by induction. So you validate or prove the base case, then you assume it's true for n, and then you say, okay, can I show that this result is true for n plus 1? Let's use one of these to prove proposition 1.3, and I'm assuming that you all have memorized proposition 1.3 and 1.2 and 1.4 and 1.5 and 1.6, right? We had 1.2 through 1.6. Proof of proposition 1.3. And we'll do that using contradiction. And now we'll probably want to be a little bit more verbose than what you might see in a book or in a paper. We may sort of write this out a little bit more thoroughly than you might see it written in a book. They sort of just leave up the scaffolding and hope that you can fill in what needs to be around. And that's what you're trying to get comfortable with as a part of this course. Reading proofs and going, where did that come from? Struggling with it and figuring out, how did he go from here to there? Oh, okay, I can make that step. Now, how did he get from this step to the third step? Okay, now I know that's, and you'll be able to then fill in the details around this maybe very concise proof that has been presented in a journal or in a textbook. Proposition 1.3, if I'm sure you have it memorized, but I don't, so I'm going to write it down again. That said that every element in our vector space V has a unique additive inverse. And here's our proof, or here is a proof. And it's in the book, but let's walk through it here. First, we need to assume that we're playing with a vector space. Let's now suppose V is a vector space. We can make that assumption. And let's also assume that we have an element from that vector space. We do have a vector. Let's just pick one. Let's say let V be an element of the vector space V. Now, what we're going to do, anticipating that we're going to use contradiction to make this proof work, I'm going to just say by way of contradiction, telling us, forewarning us what we're doing. So now, by way of contradiction, suppose that W and W prime are both additive inverses of that element V that we picked. So what have I already, I've basically said not B, because in the proposition it says, statement B says you have a unique additive inverse. I've just said no we don't, not B. I've said we have a W and a W prime. So I have two different additive inverses. That's an assumption that I'm making. And now I need to show that I end up with a contradiction as I walk through the proof. And this one basically just falls out. Now let's start with one of these additive inverses, W. Well, I can add the zero vector to that without changing it. So I could say this is now W plus 0. That's equivalent. I haven't done anything wrong now. But what is 0? Let me write 0 as V plus W prime. If W prime is indeed an additive inverse of V, by definition, V plus W prime is just the 0 element, or the 0 vector. So this is true in that statement. Now what I want to do is simply change the order in which I add these vectors. So now let me say that I want to add W with V and then add that to W prime. But by assumption, what was W plus V? That was the 0 vector, wasn't it? So now I have that's equal to 0 plus W prime, but 0 plus W prime is equivalent to W prime. What have we shown? Now we've shown that W is equal to W prime. So they have to be equal. They're not different. And that's then this contradiction that we were hoping to find. This is now a contradiction since we started with W and W prime, or we assume W and W prime were different in the first step of our proof. And that's then our contradiction. Now we've shown that they're the same. So they're not different. And that says then, therefore, the additive inverse of any element, and we'll say that's V, an element of V, is unique. Now we've talked about vector spaces. Let's pull those apart. Let's subdivide those. Let's decompose those. Let's break them down into different pieces. And that then introduces this concept of a subspace. And if you just wanted to sort of think of this as something you can picture, you might have this vector space, and inside of that is something that's also a vector space, but it's smaller in some sense. And that's a subspace. But U has to have all the properties of a subspace, of a vector space to be a subspace. I have a lot of spaces, subs going around, so make sure I say those in the right way at the right time. We have subsets, subspaces, we have vector spaces. That's good for now, right? So we have vector spaces. We can take a subset of that vector space, and then we can say, is it a subspace? Is it more than a subset of V? And to be more than a subset, it needs to have all the properties of a vector space. And then we can call it a subspace. Let me see if we can sort of make this clear, or a little more clear. Suppose this new set, U, is a subset of some vector space that we have, V. If in addition, U is also a vector space, in addition to being a subset of V, if U is also a vector space, then U is what we will call a subspace of V. And I want you to keep it clear that we're making a distinction between a subset and a subspace. There is a difference between a subset and a subspace. Or, said another way, or that is, every subset, and now I'm just implying of V, of a vector space, is not necessarily a subspace. And now the nice thing about this, in terms of trying to verify if U is a subspace, is we don't have to prove all 6 of those properties that we needed, commutivity, additivity, etc. We really only have to show 3 properties are true on U in order to show or to verify that it's a subspace. And here's what we need to do then. In order to determine if U, which now I'll be a little more verbose, which is a subset of V, is a subspace of V, we really only need to check three properties. And if you're reading along, or if you're wanting to review this at a later point, that's page 13 of Axler. That's where we're talking, or that's where this set comes from. The first thing is we need this potential subspace to have an additive identity. And what was our additive identity? Prop 1.2, what was that? That's our zero vector, isn't it? So we need this zero vector to belong to this subset. So if we can't find a zero vector, then it's not going to be a subspace. U also needs to be closed under addition. So we can just pull two vectors out of U, and if their sum falls outside of U, then we've invalidated this as a subspace. Here, then, we could say, given U and, whoops, that doesn't look much like a V, but given U and V, both in U, we need their sum to belong to U. So the addition operator needs to be a closed operator, or give us a result that ends up in that subset. We also need to check that this subset is closed under scalar multiplication. Meaning, if we take an element from our field, F, which could be the reals or complex, F could be, and if we take an element or a vector out of U, then we need that scalar, whoops, need to make sure it's lowercase here, that scaled version of our vector still lives in our subset, which would then cause, if we've got all three of these true, then U is a subspace. And we don't have to show all three, or all six. The other properties that we learned last time are needed to create a vector space. Remember, we're pulling U already out of an existing vector space. So it already, by just the consequence of it living in that vector space, it's going to obtain a lot of these other properties. So the other properties, let's say the other vector space properties are automatically satisfied since U was a subset of V. Let's look at some possible examples of this so that we can be thinking of this in a more concrete manner instead of always living in the abstract. And what's a fairly straightforward vector space to begin with? Let's just use the Euclidean plane, a two-dimensional plane. So suppose that we'll play for now with our underlying vector space as R2. So this is now our Euclidean plane. Or we could say V is now this ordered pair, xy, such that x and y are both coming to us from the set of real numbers. That's our Euclidean plane, this two-dimensional space, this piece of paper that we can draw on. Now we're feeling comfortable, right? That's our vector space. 1 as an example. U. Let's pick a subset, and let's pick one that is also pretty easy to think about. Suppose we pick this one, x0, such that x is in R. What is that? Just so that we're on the same page or on the same screen. What is this subspace? Maybe, potential. This is now a subset of R2. But what is that subset right now? That's just the x-axis, isn't it? That's pretty easy to visualize. So now we're saying, okay, is the x-axis going to be a subspace? And we would think it should be. But let's just verify it for now. So now what we want to do is we want to say, is U a subspace of V? And what do we need to do? Well, we need to show those three properties. First, we need to make sure it's a subset, and it really is. It is definitely a subset of V. And now what we want to do is check to see if the additive identity is an element of U. Is it? X can be anything on the real line. So we could pick X to be 0, and we could put that 0 right here for X, and that gives us now our additive identity. So that now this is indeed an element of our subset, U. So all we did here is we let X equal to 0, in our definition of U. And what we will learn is, or we might say, now we know that this subset is non-empty. It has at least one element in it. And this is actually the smallest subspace you can have in any subspace, is the 0 vector, 0, 0. All vector spaces have at least two subspaces, the 0 vector and the entire vector space. One subspace of R2 would be R2. Another subspace would be 0, 0. Those are pretty easy to visualize. Now we're asking, is this, let's say, horizontal line or x dimension a subspace? So we know that we have the 0 vector, or the additive identity. Now what do we need to know? Now we need to pick or see if this subset is closed for addition and closed under scalar multiplication. Let's now pick a couple of potential vectors from this subset and add them up and see if it makes sense. So let's say U1, which we'll just say is x sub 1 comma 0, and U sub 2, which is x sub 2 comma 0. Well, now we need to see if the sum, or if their addition, U1 plus U2, is in the subset U, capital U. This is now x1 plus x2 comma 0 plus 0, which is x1 plus x2, 0. Well, that's just some non-zero value possibly in the first element and 0 in the second element, and that was, by definition, what U was. So it is in U, the subset U. That's a check. What about is it closed under scalar multiplication? So now let's let A belong to the real number line, and this could be anything on that real number line. If we're trying to find counterexamples, we may want to be very specific with how we select A, but now I think we can just leave it as A is some value on the real line, or the real numbers. Let's say U1 is x1, 0, and that's obviously in our original subset. We want to check, is the scalar product of A with U1 in our subset capital U? And I think it's pretty clear, and I'm going through this in maybe more detail than you want to see. But again, that has the structure that we want. We have a 0 in the second element of our vector. So U is more than just a subset of V. It's actually a subspace of V. And you might have people say that, oh, we've now shown that this subset U is non-empty. It contained the 0 vector. U is a non-empty subset of V. That is closed under addition and closed under scalar multiplication. And that's the definition then of a subspace. So U, we could write it either in this blue sentence, or we can now just say, therefore, U is a subspace of V, because we've shown it by those three properties. What's another possible subspace that I've picked? Suppose we say W is now this vector or subset 0, comma U, comma Y, don't even know my alphabet, sorry. So Y, which is belonging to the real numbers. Subspace or not? It's very similar to the previous one, isn't it? And we could show this if we wanted to. Let's just conclude that yes, W is a subspace based on the same argument that we just presented for capital U before. What about another possible candidate? Suppose we say M is the set XX such that X is any real number. Or now our coordinates are the same. If the first coordinate is X, the second coordinate is X. And in terms of a visual image, what is this? That's this 45-degree line, isn't it, going through our Euclidean plane. And it goes through the origin, which is important, and it goes down in the third quadrant. You now have this line. We've just shown that the horizontal line was a subspace. The vertical line was a subspace. This one probably is going to be a subspace also, we would think, right? What do we need to show? Does it contain the additive identity? Is the 0 vector in this set? Yeah, we just pick X equal to 0. So this one is okay. We can say 0, 0 with X equal to 0. So that's a check. What about the closed under addition? if we say x plus y, now I'm sort of abusing the notation. Maybe I should say up here, I don't know what I want to do. Let me say this is x1, something like that. So now x plus y, I'm going to say x is now x sub 1, x sub 1. Y is supposed to belong to M. It needs to be then with equal coordinates. Our summation or addition property says we just need to add up the components. And is that in M? Yes, because those are all the same, or both components are equal. So that one works. What about closed under scalar multiplication? A needs to be an element of R, and U, let's say, is this U1, which is an element of M. AU, that's also in M, and so we've now verified that those three properties are true, and so this 45-degree line going through the origin, passing through the origin, is a subspace of the two-dimensional plane. M is a subspace. Boy, we're having a lot of positive results. Why don't we end on a downer since we're going into a long weekend? Let's look at the following. And I'm going to just tell you, this one is not. So is N, and before I even show you what N is, let me just say, ask the question, is N a subspace? So that we're not confused, I'm going to say no. Okay, so now we already know the answer in the back of the book. Why? Well, first let's figure out what N is. Suppose N is a subset of the two-dimensional plane created in the following way. Let's say it's xy such that x and y are integers. That's what that z is meaning. So this is -1, -7, 0, 6, 10. That's what this is. And x and y can belong to that. And that's obviously a subset of the two-dimensional plane. Now we have these points on these coordinates. Not everywhere, but every so often we have a point that belongs to this subset. Is that clear? We have 1, 1. We have 1, 7. We have -2, 3. Those are all a part of this subset. So this is now a subset of R2. Is the additive identity an element of N? Yeah, 0 and 0 are integers, so we could just let x equal y equals 0, so that property is okay. What about the additive? Is it closed under addition? So now if we said u is equal to, let's say, u1, u2, and maybe v is equal to v1, v2, then u plus v is equal to u1 plus v1, u2 plus v2, we could call that z1, z2, and that's also in N, isn't it? Adding and subtracting integers, it's going to give us an integer. So it's closed under addition. since these results, Z1 and Z2, are integers. Now, is it closed under scalar multiplication? A now can be all of the real numbers. That's our scalar. And let's take U equal to U1 and U2, which is in our subset of integers, which we called N. So we're pulling that from our set of vectors. But now we can actually find a counterexample. Pretty quickly. Suppose A is 1/2. A can be anything on the real line. Doesn't have to be an integer. And now we want to know and let's just say this U is 1 minus 2. Really doesn't matter what that starts with too much. I mean, you wouldn't want it to be 2 minus 2, then you wouldn't have counter-exampled anything. But it can be something pretty generic. So now we can see that A times U is this 1/2, 1 minus 2, which is now 1/2 minus 1. And that's not in our subset. So we're not closed under scalar multiplication. And this case, now we've shown that N is not a subspace of R2, even though it is a subset. Now, you're going to have the whole weekend, so you can now study up on sums and direct sums. We've just pulled apart vector spaces. We've broken them down into subspaces. Now with sums and direct sums, we want to try to put them back together, build them up again. And I don't know, maybe I'll give you a side lecture that you can watch. I don't know. I'll decide between now and Wednesday. We may start at that point on Wednesday, but here's where we're stopping today. I'll let you go since we're way over time. Thank you for your patience.